In this video, we'll study how to find arc length of a curve. We'll derive this formula. We'll solve some questions. Now, suppose we have this curve, which is given by this red curved line, and we have taken n points on these curves as P1, P2, P3 up to Pn. Now, length of this curve, it can be approximated as sum of all these line segments P1, P2, P2, P3, Pk, Pk plus 1 up to Pn minus 1, Pn. So we can say this length of this curve, it can be approximated as sum of all these lengths Pk to Pk plus 1, where the value of k varies from 1 to n minus 1. So roughly, if we add all these lengths, we'll get an approximate length of this curve. Now we know that distance between any two points, it is given by under root of x2 minus x1 whole square plus y2 minus y1 whole square. Now suppose between these 2 points, pk and pk plus 1, difference of their x coordinates is delta xk and difference of their y coordinates is suppose delta yk, then we can write this L as this summation k varies from 1 to n minus 1 under root of delta xk whole square plus delta yk whole square. Now what we'll do is we'll take delta xk common. So now we can write this L as this summation k varies from 1 to n minus 1 under root of 1 plus delta yk upon delta xk whole square into delta xk. Now, if we increase number of points, then this approximation will keep getting better. So basically, if we take infinite points on this curve, then this approximate length will be equal to actual length of this curve. So we can write actual length of this curve as this limit n tends to infinite summation k varies from 1 to n minus 1 under root of 1 plus delta yk upon delta xk whole square into delta xk. Now when we take this limit n tends to infinite, this summation, it changes into this integral. Now this is under root of 1 plus, now when delta x is very small, then in that case this delta y upon delta x is nothing but it is slope of tangent at this point. So basically it will be dy by dx whole square into dx, and then limits of this integration, we are applying these limits from x equal to a to x equal to b, because we are interested in finding out length of this curve between a and b. So it will be this a to b under root of 1 plus dy by dx whole square into dx. So basically, if we have any curve y equals to fx and we have to find length of this curve from a to b, then this length, it is given by this integral from a to b under root of 1 plus dy by dx whole square into dx. Now we can write this formula in a couple of different ways. At times, we'll write this formula as this integral from a to b and simply under root of delta x square plus delta y square. So we'll simply write this as dx square plus dy square. And at times, when x and y, they are some function of parameters, say x is some f1t, y is some f2t, then we can write this length as this integral, and we'll find out values of t1, t2 from these relationship, and it will be under root of dx by dt whole square plus dy by dt whole square into dt. We can write this formula for polar coordinates also. Now we know that for polar coordinates, x is r cos theta and y is r sin theta. Now if we find dx upon d theta, it will be minus r sin theta plus cos theta into dr by d theta. And if we differentiate this y with respect to theta, it will be r cos theta plus sin theta into dr by d theta. Now we square and add them, we can write dx upon d theta square plus dy upon d theta square will be r square sin square theta plus cos square theta will be 1 plus, now here sin square theta plus cos square theta, again it will be 1, so it will be dr upon d theta whole square. Now here it is minus 2 sin theta cos theta r dr d theta, and here it is plus 2 sin theta cos theta r dr d theta, which will cancel. So that's how we can find dx upon d theta square plus dy upon d theta square. Now simply we can write length of this arc as this integral, and we'll find appropriate values of theta 1 and theta 2 using this relationship, and under root of dx upon d theta square plus dy upon d theta square, which is r square plus dr upon d theta square into d theta. And this is how we find arc length in case of polar coordinates. Now let us take an example. Say for example, we have a curve which is given by 24xy and it is equal to x to the power 4 plus 48, and we have to find length of this curve between x equal to 2 to x equals 4. Now this, first we'll write y is x cubed by 24 plus 2 upon x. Now we'll find dy by dx. Now dy by dx, it will be 3x square, so it will be x square by 8 minus 2 upon x square. Now once we have dy by dx, we can write length of this curve. It will be this integral from 2 to 4 under root of 1 plus x square by 8 minus 2 upon x square whole square into dx. Now this is this integral from 2 to 4, and this is under root of 1 plus, now this is x square upon 8 whole square plus 2 upon x square whole square, and then minus 1 by 2 into dx. Now 1 minus 1 by 2 is plus 1 by 2. So we can write this as this integral from 2 to 4 and then under root of x square by 8 whole square plus 2 by x square whole square plus 1 by 2 into dx. Now this is nothing but a square plus b square plus 2ab. So we can simply write this as this integral from 2 to 4 under root of, now this is x square by 8 plus 2 upon x square dx, which is this integral from 2 to 4 x square by 8 plus 2 upon x square into dx. Now we integrate this function. So it will be this x cube by 3, which is 1 by 24, and then 4 cube minus 2 cube, and here it will be minus 1 by x. So it will be plus 2 and then minus 1 by 4 plus 1 by 2. Now this is 64 minus 8, 56. 56 upon 24. And here it will be plus 1 by 2, which is 68 by 24 or 17 by 6. So arc length of this curve between 2 and 4, it is 17 by 6. Now we'll take second question, and here we need to find arc length of a catenary. Now we have already studied catenary in one of the previous videos. So I'll provide the link to that video in the description. Now we already know that equation of catenary is given by y equals a by 2 into e to the power x upon a plus e to the power minus x upon a, where value of x varies from 0 to a. And this catenary, it almost looks like a parabola, but it's an equation which is different from parabola, and this is the actual shape of hanging objects. Now we find dy by dx. Now dy by dx will be a by 2 e to the power x upon a into 1 by a, and then minus e to the power minus x upon a into 1 by a. Now this 1 by a, it will cancel. So basically dy by dx is 1 by 2 e to the power x upon a minus e to the power minus x upon a. Now we'll find its arc length. Now it will be this integral from 0 to a and then under root of 1 plus dy by dx whole square. So it will be this 1 by 4 and then e to the power x upon a minus e to the power minus x upon a whole square into dx. Now this L is this integral from 0 to a and then under root of, this is 1 plus 1 by 4 and this is e to the power x upon a square plus e to the power minus x upon a square, and then this is minus 2 into dx. Now this is minus 1 by 2 and 1 minus 1 by 2 is plus 1 by 2. So basically this is this integral from 0 to a under root of 1 by 4 e to the power x upon a plus e to the power minus x upon a whole square into dx. Now we can write this as 1 by 2 and then integral of e to the power x upon a plus e to the power minus x upon a into dx. Now this is 1 by 2 and it is e to the power x upon a into a from 0 to a and then plus e to the power minus x upon a and then it will be this minus a from 0 to a. Now this is 1 by 2 and this is a into e minus a, and here it will be minus a into e to the power minus 1 plus a. Now this a and a, it will cancel. So arc length of a catenary, it is given by a by 2 into e minus 1 upon e. Now let us take another example. We have to find arc length of x to the power 2 by 3 plus y to the power 2 by 3 equals 4 from x equal to 1 to x equals 8. Now what we'll do is we'll write this equation in terms of parametric coordinates. Now we can write this x as 8 sine cube theta and this y as 8 cos cube theta. Now we can write dx upon d theta as 24 sine square theta into cos theta, and dy by d theta is minus 24 cos square theta into sin theta. Now if we find dx upon d theta square plus dy upon d theta square, now here we'll take 24 sin theta into cos theta whole square common, and then it will be sin square theta plus cos square theta, which is 1. So it will be equal to 24 sin theta into cos theta whole square. Now we can write length of this curve as this integral. Now when x is 1, sine theta is 1 by 2. And therefore theta is pi by 6. And if x is 8, sine theta is 1. So it will be this integral from pi by 6 to pi by 2. And then under root of this value. And under root of this value is 12 sine 2 theta into d theta. Now this is 12. And integral of sine 2 theta is minus cos 2 theta upon 2 from pi by 6 to pi by 2. Now this is minus 6. And if we put upper limit, it will be this cos pi. Cos pi is minus 1. And then minus cos pi by 3. And cos pi by 3 is 1 by 2. So this value will be 9. So arc length of this curve between 1 and 8 is 9 units. In projectile, you must have studied a lot of things. Time of flight, range, maximum height. But rarely in projectile we study its arc length. So here we'll find length of this curve or arc length of this projectile. Now we know that at any time t, x coordinate of this projectile, it is given by u cos theta into t, and its y coordinate is given by u sin theta into t minus half g t square. So what we are doing is we are trying to find arc length of this projectile using parameter t. So we have to find this arc length for its entire time of flight, and time of flight is simply 2u sin theta upon g. Basically for time of flight we put y as 0 and then simply you'll get time as 2u sin theta upon g. Now basically we'll find dx upon dt. Now dx upon dt is u cos theta and dy upon dt is u sin theta minus gt. Now we can write length of this projectile as this integral from 0 to this time of flight and then under root of u cos theta square plus u sin theta minus gt square into dt. Now we need to solve this integral, and what we'll do is we'll take u cos theta common. We'll write L as u cos theta and then this integral from 0 to t and then under root of 1 plus now will be this tan theta minus gt upon u cos theta whole square into dt. Now what we'll do is we'll let this tan theta minus gt upon u cos theta as some variable, say z. Now we'll try and find its limit. Now if t is 0, then the value of z is tan theta, and if t is this time of flight, then the value of z will be tan theta minus g upon u cos theta into time of flight, and time of flight is 2u sin theta upon g. Now g will cancel, u will cancel, so it will be this minus tan theta. So we can write this L as u cos theta and then this integral from tan theta to minus tan theta under root of 1 plus z square into, now we have to replace dt with dz. Now here if we differentiate this, we'll get minus g upon u cos theta dt and it will be equal to dz. So it will be dz upon minus g into u cos theta, and we'll write this as u cos theta square. Now we'll take this minus sign, then we can interchange the limits. So we can write this L as u square cos square theta upon g, and then this integral from minus tan theta to plus tan theta into under root of 1 plus z square into dz. Now this is an even function, so we can write L equals 2u square cos square theta upon g into this integral from 0 to tan theta under root of 1 plus z square into dz. Now this is L and this is 2u square cos square theta upon g, and integral of under root of x square plus a square is z under root 1 plus z square plus a square upon 2 log z plus under root of z square plus 1, this integral from 0 to tan theta. Now this is u square cos square theta upon g into, now this is tan theta into 1 plus tan square theta is secant theta. So it will be sin theta upon cos square theta log tan theta plus secant theta minus, now if z is 0, this is 0, and this is log 1, which also is 0. So basically length of projectile is given by u square cos square theta upon g sin theta into cos square theta plus log tan theta plus secant theta. And if we want, instead of writing it in terms of log, we can write it in terms of sine hyperbolic. So it will be sine hyperbolic inverse of tan theta. And this is the formula for arc length of a projectile. And since this formula is complicated, we don't study it, but proving this formula is definitely a delight.